understanding of physics upside down. Objects that force us to rewrite textbooks and reconsider everything we thought we knew about the cosmos. They're called gravastars. Gravitational vacuum stars. Gravitational vacuum condensates. Ghosts of collapse. They have many names, but the essence is singular. They are potentially the most extreme, the most incredible, the most terrifying objects in the universe. And they might be real. Black holes. Forget about them. For a century we've frightened ourselves with black holes, these all-devouring monsters of spacetime, these cosmic vampires from which nothing can escape. We've trembled before them. Made movies about them. Written books. Created computer models of their accretion disks, their event horizons, their singularities. But what if all this time we've been afraid of the wrong thing? What if black holes are just a simplified version of reality? A convenient mathematical abstraction? An approximate solution to equations that works in theory but fails in the real cosmos? What if out there, in the actual universe we inhabit, something far stranger exists? Something that makes black holes look tame by comparison. Welcome to the world of gravastars, objects that may be even more terrifying, even more mysterious, even more incredible than anything we've ever imagined. This is a story about how science moves forward, stumbling in darkness. About how every truth turns out to be merely a stepping stone to an even stranger reality. About how the universe again and again proves itself more inventive than our wildest fantasies. Are you ready to gaze into an abyss that gazes back? Let us begin with what seemed like absolute truth. With what we accepted as fact. With black holes. Picture a star. Not an abstract point of light in the night sky, but a gigantic thermonuclear reactor the size of 1,000,000 Earths. A ball of plasma where every second millions of tons of hydrogen transform into helium, releasing energy capable of illuminating planetary systems trillions of kilometers around. This isn't just light. This is war. A battle of titans. A confrontation between two fundamental forces of nature. On one side, gravity. Merciless. Relentless. Forever pulling everything toward the center. It wants to compress the star into a point, to turn it into nothing, to crush every atom under unimaginable pressure. Gravity is a cosmic press, working without pause, without fatigue, without mercy. On the other side, thermonuclear pressure. The fury of fusion reactions. Photons and particles bursting outward with such force that they keep the star inflated, prevent it from collapsing. This is a shield against gravity. A defense against collapse. For billions of years these forces remain in balance. They dance a cosmic dance. They maintain a fragile balance between existence and annihilation. But nothing lasts forever. When the fuel runs out, when the thermonuclear furnace cools, when the last hydrogen atoms convert to heavier elements, the shield falls. The defense crumbles. And gravity wins. Collapse. This word doesn't convey even 1/100th of the horror of what occurs. A star that existed for billions of years implodes in mere seconds. Matter falls inward at velocities approaching light speed. The pressure becomes so monstrous that the electron shells of atoms shatter. Protons and electrons merge into neutrons. The very fabric of space begins to deform, distort, fold. And at the very end, when even neutron matter cannot resist gravity, when even the Pauli exclusion principle surrenders, she emerges. The black hole. More precisely, that's what we were taught. That's what textbooks said. That's what professors explained in universities around the world. A black hole is a place where gravity wins definitively. Where all the stars' mass collapses into an infinitely small point, a singularity. Where density becomes infinite and the laws of physics as we know them cease to function. Around this singularity forms an event horizon, a boundary of no return, a point of no return. To cross it means to vanish forever from the observable universe. Beautiful theory. Elegant mathematics. A solution to Einstein's equations found by Karl Schwarzschild back in 1916, when the First World War raged in Europe and Einstein himself had barely finished his general theory of relativity. For a century we believed this. For a century we built all of relativistic astrophysics on this foundation. But what if it's too simple? What if nature abhors infinities? What if the singularity is not reality but a mathematical artifact? What if there, where we see a black hole, something else exists? Physicists don't like infinities. They're dirt in the cleanliness of their mathematics. They're a warning signal indicating that the theory is breaking down somewhere, exceeding the limits of applicability. When infinities appear in your equations, it usually means one thing: you've missed something. You haven't accounted for some important effect. You've entered a domain where your theory no longer works. And black holes are full of infinities. Infinite density at the center. Infinite curvature of spacetime. Infinite redshift at the event horizon. These mathematical monsters lurk in the very heart of black hole theory, and physicists have never felt comfortable with them. Richard Feynman, one of the greatest physicists of the 20th century, once said, "If a theory gives infinity, then something's wrong with the theory." He understood. Nature is finite. The universe may be strange, paradoxical, counterintuitive, but not infinite at a specific point in space. And yet for decades we tolerated these infinities. We closed our eyes. We told ourselves, well, we don't have a better theory. We hid the singularity behind the event horizon, as if that solved the problem. We said, nothing can escape from inside, so we don't need to worry about what happens there. But this is self-deception. Physics must work everywhere. The laws of nature cannot simply turn off in certain places. The singularity is not a solution, it's an admission of defeat. It's a white flag thrown up in the face of ignorance. And some physicists understood this. They searched for alternatives. They tried to find ways to avoid the singularity. They believed there must exist something else, some structure, some mechanism that stops the collapse before it reaches infinite density. Wormholes. Planck stars. Boson stars. Fermion balls. Dozens of exotic objects were proposed over the decades. Each with its merits. Each with its problems. And then, in 2001, at the beginning of the new millennium, when the world was still recovering from the attacks of September 11th, two physicists published a paper that should have changed everything. Pauwel Mazur and Emil Motola. Two names that few know outside a narrow circle of relativists. They proposed something radical. Something revolutionary. Something so strange that most of their colleagues simply didn't believe it. They called it a gravitational vacuum condensate. Or, more briefly, a gravistar. Scientific revolutions are rarely loud. They don't happen with an explosion, with fanfare, with headlines on the front pages of newspapers. More often they begin quietly, with a paper in a specialized journal that only a few dozen people will read. With an idea so strange that it's either ignored or ridiculed. The paper by Mazur and Mottola was exactly like that. Gravitational Condensate Stars and Black Holes, that was the title of their work. A dry, technical name concealing an idea capable of overturning astrophysics. What did they propose? Imagine a collapsing star. Gravity compresses it. Matter falls inward. Pressure builds. Temperature soars to billions of degrees. Everything is heading toward the formation of a black hole. But in the last moment, in the microsecond before the event horizon forms, something happens. Something fundamental. Something connected to the very nature of spacetime itself. The vacuum changes phase. Sounds absurd. Let's understand this. In quantum field theory, vacuum is not emptiness. It's not the absence of everything. Vacuum is the lowest energy state, filled with virtual particles, fluctuations, quantum effects. Vacuum is alive. It seethes with quantum activity, though we don't see it. And like any quantum field, vacuum can exist in different phases. Just as water can be ice, liquid, or vapor, three different phases of the same substance. Under normal conditions, vacuum is in one phase. But what happens under extreme conditions? Under the monstrous pressure of a collapsing star? Under the warping of spacetime close to critical? Mazur and Mottola hypothesized, vacuum can transition to another phase. A phase with negative pressure. A state that creates anti-gravity. Yes. Anti-gravity. Not repulsion in the usual sense, but something more subtle, more fundamental, an effect similar to dark energy, that same mysterious force accelerating the expansion of the universe. And this anti-gravity stops the collapse. Right at the threshold. Millimeters from where the event horizon should have formed. The star freezes in a state of almost collapse. Almost black hole. But not quite. This is a gravastar. Try to visualize this. Try to see with your mind's eye the structure of an object that defies intuition. On the outside, a thin shell. Incredibly dense. Matter compressed to such a degree that protons and neutrons practically touch. A hardness exceeding everything we know. A strength that cannot be measured in ordinary units. This shell has a thickness, possibly, of a Planck length, the smallest meaningful scale in physics, 10 to the minus 35 meters. Thinner than an atom by 10 to the 20th times. Thinner than a proton by billions of times. And yet this unimaginably thin shell holds everything together. It is the barrier between our reality and, what? Inside, vacuum. But not ordinary vacuum. Vacuum in an exotic state. Spacetime in a phase with negative pressure, with energy that pushes outward rather than pulling inward. It's like a bubble of anti-gravity, enclosed in the hardest shell in the universe. No singularity at the center. No point of infinite density. No place where physics stops working. There is only strange vacuum pressing from within, and matter compressed to the limit, holding that vacuum captive. Balance of forces. Balance again. But completely different from an ordinary star. In an ordinary star, thermonuclear pressure opposes gravity. Here, the quantum pressure of vacuum opposes the attempt of matter to collapse further. This is equilibrium on a knife's edge. Dynamic stability on the brink of impossibility. From the outside, a gravastar looks almost identical to a black hole. Almost. It possesses mass. It warps spacetime around itself just the same. It attracts matter, light, everything that comes too close. Its gravitational field is indistinguishable from that of a black hole of the same mass. But there is one critical difference: a gravastar has no event horizon. The boundary that appears to be a horizon is actually a solid surface. Incredibly close to where the horizon would be, but still not it. A photon's millimeters. Planck distances. But in physics, even such microscopic differences can have colossal consequences. Information doesn't disappear in a gravastar. It can reflect from the surface. Monstrously redshifted, yes. Stretched in time beyond recognition, yes. But not lost forever, as in a black hole. This solves one of the most agonizing paradoxes of modern physics. Stephen Hawking. A name that became synonymous with black holes. A physicist who devoted most of his life to studying these objects. And it was he who discovered the problem that tormented him until his death. In the 1970s, Hawking made an astounding discovery: black holes aren't completely black. They radiate. They evaporate. Slowly, incredibly slowly, but inevitably. Quantum effects near the event horizon birth pairs of virtual particles. One falls inside, the other flies away. To an external observer, this looks like radiation from the black hole. Hawking radiation. A triumph of theoretical physics. A connection between general relativity, quantum mechanics, and thermodynamics. But hidden in this discovery was a time bomb. If a black hole evaporates completely, and theory predicted that sooner or later this would happen, then what happens to the information about all the matter that fell inside? Information about every atom, every particle, every quantum state. According to quantum mechanics, information cannot simply disappear. This is a fundamental principle. The law of information conservation. To violate it means to destroy the entire edifice of quantum theory. But if a black hole evaporates through Hawking radiation, which is completely random and carries no information about what fell inside, where does the information go? The information paradox in black holes. A problem that split the physics community for decades. A battle of titans, relativists versus quantum physicists. Years of debates. Kilometers of written paper. Hundreds of articles and counter-articles. Hawking initially asserted that information really is lost. This shook the foundations of physics. Other physicists, especially Leonard Susskind and Gerard T. Hooft, fiercely disagreed. The black hole wars began, an intellectual battle lasting decades. Eventually, Hawking admitted his error. In 2004, he publicly agreed that information must be conserved. But exactly how it's conserved in a black hole? That remained a mystery. Gravastars offer an elegant solution. If there's no event horizon, if there's no true black hole, then there's no paradox. Information remains on the surface of the gravastar. Yes, monstrously distorted. Yes, stretched by time. But not lost. Problem solved. In principle, yes. In practice, everything is much more complicated. Because information stored on a surface of Planck density is fundamentally inaccessible. We cannot read it. We cannot decipher it. For all practical purposes, it's lost, even if it formally exists. It's like saying that information about a burned book is conserved in the atoms of smoke and ash. Technically true. Practically useless. But for physics, this matters. It's the difference between a theory that's consistent with fundamental principles and a theory that violates them. And gravastars are consistent. Black holes are not. Or at least their consistency requires additional, not fully understood mechanisms. Science is not a monolith. It's not a single army marching toward truth in orderly rows. Science is a battlefield of ideas, where every theory must fight for survival. Where skepticism is not a flaw but a necessity. Where every claim meets resistance. And the idea of gravastars met considerable resistance. Too exotic, said critics. Where's the proof? Where are the observations? Where are the experiments? Vacuum phase transition. Under what conditions? What physics describes this? What equations? A shell of Planck thickness? How can it be stable? Why doesn't it collapse? Why doesn't it rupture? Questions poured down like hail. And many of them were fair. Howell Mazur and Emil Motola relied on semi-classical reasoning. They extrapolated known physics into a domain where, perhaps, a completely new theory is needed. They made assumptions about the behavior of vacuum under conditions we've never observed and possibly never can reproduce. Quantum gravity, the theory that should unite general relativity and quantum mechanics, still hasn't been constructed. We don't know exactly how spacetime behaves on Planck scales. We build guesses, models, hypotheses. But there's no solid knowledge. And gravastars are based on these shaky foundations. Moreover, many physicists pointed to stability problems. If such an object forms, will it be stable? Or will it instantly collapse into a true black hole? Or explode, torn apart by internal pressure? Numerical simulations gave contradictory results. Some showed that gravastars could be stable. Others, that they're unstable at the slightest perturbation. Still others demonstrated that everything depends on model details. On subtleties of the equation of state for matter in the shell. Debates continued. Continue to this day. But skepticism is not rejection. It's a demand for proof. And this is exactly what drives science forward. Over 2 decades since the initial paper, dozens of modifications of the gravastar idea appeared. Physicists are inventive folk. They took the basic concept and began experimenting with it, changing parameters, exploring alternative scenarios. Gravastars with anisotropic shells, where pressure differs in radial and tangential directions. This makes the construction more stable but adds complexity to the mathematics. Gravastars with multiple shells, an onion-like structure where layers of normal matter and exotic vacuum alternate. A matryoshka of phase transitions. Charged gravastars, objects with electric charge, adding electromagnetic effects to gravitational ones. This makes them even stranger but perhaps more realistic. Rotating gravastars, after all, real stars rotate, and post-collapse objects should rotate too. Angular momentum adds additional complexity, additional forces, additional ways to stabilize or destabilize. Each modification was investigated. each analyzed mathematically, each checked with numerical simulations. And gradually, slowly, the picture became clearer. Gravastars possibly can exist. Possibly are stable. Possibly form in the real universe. But possibly is not the same as definitely. Proof was needed. Observations were needed. Signs that would distinguish a gravastar from a black hole were needed. And here begins the most intriguing part. How do you distinguish a gravastar from a black hole? It's a question that sounds simple, but the answer is devilishly complex. Both objects are massive. Both are compact. Both warp spacetime almost identically. Both capture light, matter, everything that comes too close. To an astronomer observing from afar, they look practically the same. But practically is the key word. There are subtle differences. Barely perceptible. Requiring our most sensitive instruments and most sophisticated analysis techniques. But they exist. The first difference, gravitational wave echoes. When two black holes merge, they create ripples in the fabric of spacetime. Gravitational waves race through space at light speed. We've learned to detect them, LIGO and Virgo, giant interferometers capable of registering space stretching smaller than the width of a proton. Black hole mergers produce a characteristic signal, a chirp, rising frequency, then sharp decay as the new, merged black hole settles down. This signal is predicted in detail by general relativity. We know what it should look like. But if one or both merging entities are gravastars, then there should be echoes. Reflections from the solid surface instead of disappearance behind the horizon. Additional oscillations, additional components in the signal. Physicists have searched for these echoes. They've combed through detector data. Applied sophisticated processing algorithms. Some claim to have found hints of these echoes. Others said these were statistical fluctuations, noise, processing artifacts. Debates continue. Data is inconclusive. We're at the edge of our instrument's sensitivity. The second difference, quasi-periodic oscillations in X-ray emission. When matter falls onto a compact object, it forms an accretion disk, a spiral of superheated gas that gradually loses energy and angular momentum, approaching the central body. This disk radiates in the X-ray range. And in this radiation, oscillations can be detected, periodic changes in brightness. They arise from the motion of matter in strongly curved spacetime near the compact object. The frequencies of these oscillations depend on details of the gravitational field. And if the object at the center is a gravastar with a solid surface instead of an event horizon, the frequencies should differ. Slightly. But measurably, if our telescopes are accurate enough. Again, observations at the edge of possibility. Again, debates about the significance of results. The third difference, gravitational waves from oscillating objects themselves. If a gravastar is perturbed, say, it swallowed a small portion of matter or was subjected to a gravitational shock from a passing star, it should ring like a bell. Oscillate. But the character of these oscillations differs from those of a black hole. A black hole has characteristic ringing frequencies, quasi-normal modes. They depend only on mass and spin. Mathematically, this is beautifully described by the perturbed Kerr metric. A gravastar's frequencies are different. They depend on the shell structure, on the equation of state of matter, on details of the internal vacuum state. The spectrum is richer, more complex. Detecting these oscillations means distinguishing the objects. But this requires incredibly precise measurements. And, critically, a nearby event. Gravitational waves from an oscillating gravastar are weaker than from a merger and harder to detect. The fourth difference, shadows in Event Horizon Telescope images. In 2019, humanity first saw the shadow of a black hole. More precisely, an image of M87-, the supermassive black hole at the center of galaxy M87. A dark region in the center, surrounded by a glowing ring of the accretion disk. This was a triumph. An image consistent with general relativity predictions. Confirmation of event horizon existence. Or was it? If the object at the center is a gravastar, its shadow should look just slightly different. The size of the dark area slightly differs. The shape may be somewhat deformed. Details of brightness at the boundary have a different character. These differences are so small that even EHT's capabilities may be insufficient for unambiguous distinction. Even more sophisticated instruments are needed. Longer interferometry baselines. More telescopes in the array. More sensitive receivers. But one day, perhaps soon, we may be able to say for certain. Are there real gravastar candidates? The billion-dollar question. Or rather, the billion-light-year question. Every time a compact object merger is detected, every time a new black hole candidate system is discovered, groups of physicists begin analyzing, could this be a gravastar? GW190521, a merger of two massive objects creating a gravitational wave detected in 2019. The component masses fell into the forbidden zone, a range where black holes shouldn't form according to standard stellar evolution scenarios. This anomaly required explanation. Could these have been gravastars? Some physicists argued, yes. Gravastars can form with masses unattainable for ordinary black holes of stellar origin. Exotic physics creates exotic objects. Others remain skeptical. Alternative explanations, intermediate black holes formed through non-standard mechanisms, mergers in dense star clusters, dynamical interactions, could also explain observations. GW170817, a neutron-star merger, the first event where gravitational waves were accompanied by electromagnetic radiation. A kilonova flash, gamma-ray burst, afterglow across all ranges. A treasure trove of data for astrophysicists. Analysis showed the merger product was a massive compact object. Possibly a black hole. Possibly a hypermassive neutron star. Possibly, a gravastar. Again debates. Again uncertainty. And so with each new event. Data permit interpretation. But don't demand it. Gravastars remain a possibility, not a necessity. The problem is that the differences are too subtle. Our instruments, for all their incredible sensitivity, operate at the limit. We see objects from billions of light-years away, through distorted spacetime, through interference from dozens of noise sources. Extracting the tiny signal indicating a gravastar from this cacophony is a task of colossal complexity. But we don't give up. Suppose for a moment that gravastars are real. That they exist in the universe, hiding under the mask of black holes. What happens then? What makes them more terrifying than black holes? This isn't a question of literal danger. Neither a gravastar nor a black hole poses a threat to Earth. The nearest black hole is thousands of light years from here, and a gravastar at that distance wouldn't harm us either. No. The terror here is intellectual. Philosophical. It's the terror before a reality even stranger than we thought. Before a universe that again proves more inventive than our imagination. Let's start with the surface. A black hole has no surface. The event horizon is not a material boundary, it's simply a place in spacetime from which there's no return. Crossing it doesn't mean hitting something. It means entering a region from which your trajectory inevitably leads to the singularity. For a freely falling observer, crossing the horizon might not be remarkable at all, only later would they realize they cannot return. A gravastar has a surface. Solid. Material. You can collide with it. And that collision would be specific. Imagine you're falling toward a gravastar. Accelerating under monstrous gravity. Speed increasing. Approaching light speed. Space-time around you increasingly distorting. Time slowing relative to a distant observer. And then, impact. But what kind of impact? With what density of matter do you collide? Matter in a gravastar's shell is compressed to Planck density, about 10 to the 96th kilograms per cubic meter. That's 10 to the 80th times denser than an atomic nucleus. This is density at which quantum gravity becomes the dominant force. Colliding with such a surface means colliding with matter so dense that the concept of collision loses meaning. You won't simply be torn apart. You'll be torn into atoms. Atoms torn into particles. Particles decomposed into quantum foam. The impact energy at relativistic velocities would transform you into a flash of radiation, so bright and hot that to an external observer it would look like a micro-explosion on the object's surface. A black hole is more merciful. There you're simply consumed. Information about you disappears behind the horizon, or is preserved in some mysterious way, but in any case you're gone. A gravastar though, a gravastar would smear you across its surface in a two-dimensional holographic pattern of quantum information. This isn't just death. This is quantum annihilation. But there's something even more frightening. What happens if a gravastar destabilizes? Imagine, the balance of forces is disrupted. Maybe the object swallowed too much matter. Maybe it merged with another compact object. Maybe simply enough time passed for quantum fluctuations to disturb the fragile equilibrium. The shell begins to fail. Inside, vacuum with negative pressure. Anti-gravity, restrained by the shell. What happens when containment weakens? One scenario, collapse. The shell can't hold, implodes inward, and the gravastar transforms into a true black hole. A singularity forms, the event horizon finally establishes itself. The object transitions from one exotic state to another. To an external observer, this might look like a sudden change in gravitational properties. Quasi-normal modes change. Echoes disappear. The object becomes more black. Another scenario, explosion. Internal pressure ruptures the shell. Exotic vacuum bursts outward. And then something occurs for which we have no good analogies. This isn't a supernova, there a star explodes, matter flies apart, energy from thermonuclear fusion and gravitational collapse is released. This isn't a gamma-ray burst, though there will be radiation, very intense radiation. This is an explosion of the fabric of spacetime itself. A release of vacuum energy locked in an exotic state. A quantum phase transition in reverse, occurring catastrophically fast. The energy. The object's mass multiplied by the speed of light squared. E equals mc squared. All of it, or a significant portion of it, released in milliseconds. For an object of several solar masses, this means energy equivalent to 100 of the most powerful supernovae occurring simultaneously. A gamma-ray flash capable of sterilizing planets within hundreds of light-years. A gravitational shock capable of disturbing a galaxy's structure. This is purely hypothetical, of course. We don't know if gravastars can explode. We don't know if they're stable long-term. We don't even know for certain if they exist. But if they do, if they can explode, then the universe harbors time bombs, each capable of releasing energy exceeding anything we've observed in space except the Big Bang itself. Sleep well. Let's return to the information problem. To Hawking's paradox. In a black hole, information, about every atom that fell inside, about every quantum state, is presumably conserved. But how? Where? In what form? String theory offers the holographic principle: all information is encoded on the event horizon, in a two-dimensional structure invisible to an external observer. This is mathematically elegant but physically enigmatic. In a gravastar, everything is simpler and more complex simultaneously. Information remains on the surface. Literally. Every particle falling onto a gravastar interacts with the incredibly dense matter of the shell. The quantum state of the falling matter imprints itself on the quantum state of the surface. This isn't a metaphor. This is a physical process. Quantum entanglement between falling matter and shell matter. Information about what fell is distributed across the entire surface, mixing with already existing information. As the gravastar evaporates through Hawking radiation, yes, gravastars evaporate too, though the process differs from black holes. Information gradually releases back. Incredibly slowly. Incredibly entangled. But not lost. Paradox solved. In principle, yes. In practice, everything is much more complicated. Because information stored on a surface of Planck density is fundamentally inaccessible. We cannot read it. We cannot decode it. For all practical purposes, it's lost, even if it formally exists. It's like saying information about a burned book is conserved in smoke and ash atoms. Technically true. Practically useless. But for physics, this matters. It's the difference between a theory consistent with fundamental principles and one that violates them. And gravastars are consistent. Black holes aren't. Or at least their consistency requires additional, not fully understood mechanisms. If gravastars exist, how many are there? This is a question impossible to answer without observations. But we can speculate. Every massive star collapsing at life's end potentially could form a gravastar instead of a black hole. Conditions must be suitable: sufficient mass, correct metallicity, certain rotation rate. But if conditions are met, gravastar. How many massive stars have collapsed since the first stars formed in the universe? Billions. Trillions. In our galaxy alone, hundreds of millions. If even 1% of them formed gravastars, we're talking millions of these objects just in the Milky Way. In the observable universe, quintillions. An army of gravastars masquerading as black holes. Each, a bomb of quantum vacuum. Each, an information repository. Each, a mystery awaiting solution. And that's only stellar masses. What about supermassive objects in galaxy centers? Sagittarius A star, the object at our galaxy's center, with a mass of 4 million suns. We think it's a black hole. But what if it's a gravastar? Differences would be even subtler at such scales. Even harder to verify. But the consequences are colossal. A supermassive gravastar would have different structure, different formation history, different influence on the surrounding galaxy. Understanding that galaxy centers contain gravastars, not black holes, would rewrite galactic evolution theory. And if they explode, a supermassive gravastar explosion would destroy the galaxy completely. Scatter stars across intergalactic space like a dandelion blown by wind. Do we observe such events? Are there galaxies that suddenly, catastrophically disintegrated? Honestly, we don't know what to look for. We don't know what a galaxy's death from central gravastar explosion looks like. We're not even sure it's possible. But if it is, the universe is even more terrifying than we thought. To definitively resolve the question of gravastar existence, we need better tools. More sensitive detectors. Capable of registering the subtlest differences in gravitational waves. LIGO and Virgo are engineering triumphs. But they operate at high frequencies. Detecting stellar mass mergers. They're blind to low-frequency signals, to events involving supermassive objects. This is where LISA enters the stage. Laser Interferometer Space Antenna. A space-based gravitational wave detector, launch planned for the 2030s. 3 satellites forming a triangle with sides of 2.5 million kilometers. Flying in formation, maintaining position with nanometer precision. Exchanging laser beams, tracking the tiniest changes in distances between them. LISA will be sensitive to low frequencies. To massive black hole, or gravastar, mergers. To events in galaxy centers. To processes inaccessible to ground-based detectors. And LISA may provide the definitive answer. Because differences between gravastars and black holes are more pronounced in the low-frequency range. Echoes more noticeable. Quasi-normal modes more separated. Statistical significance higher. If gravastars exist, LISA will find them. Or at least find signs that cannot be ignored. This isn't just a question of curiosity. It's a question of understanding gravity's nature, spacetime's nature, reality's very nature. The Event Horizon Telescope showed we can image shadows of compact objects. But EHT resolution is limited. Baseline size, Earth's diameter. We can't make it larger unless we build telescopes in space. And that's exactly what's being planned. Projects for space interferometers operating in millimeter and submillimeter ranges. Satellites in Earth orbit or even solar orbit, creating baselines millions of kilometers long. With such resolution, we could see not just the shadow but structural details near the horizon, or its absence. We could distinguish a gravastar's solid surface from a black hole's event horizon. We could see photon orbits, light trajectories captured in stable or quasi-stable orbits around the object. Their structure depends on whether there's a horizon or solid surface. We could observe accretion with unprecedented resolution. See how matter falls onto the object, how it interacts with the surface, or disappears behind the horizon. Process dynamics differ, and with sufficient resolution these differences become visible. Technologies exist. Physics is understood. Only time, money, and will are needed. And, of course, a bit of luck. Because even the best instruments are useless if nature doesn't provide suitable objects for study. Can we recreate gravistar conditions on Earth? Even in principle? Answer, no. Absolutely not. Not even close. Pressures necessary for vacuum phase transition, if such a transition is even possible, lie beyond anything we can create. Particle accelerators, even the most powerful, even future colliders, reach energies far from the Planck scale. The difference, about 15 orders of magnitude. It's like comparing an atom's size to the solar system's size. We cannot create a gravistar. We cannot even approach its formation conditions. But we can build models. Computer simulations. Numerical solutions to Einstein's equations with various assumptions about matter and vacuum behavior. And we do this. Hundreds of physicists worldwide work on gravistar models. Explore different scenarios. Predict observational signatures. Prepare the ground for experimental verification. Because ultimately science is a dialogue between theory and observation. Theory proposes ideas. Observation tests them. And in this dance, this interaction, knowledge is born. We approach questions that go beyond physics. Questions about reality's nature, about the limits of knowledge, about what it means to exist. Gravistars, if they're real, exist at the very boundary of the knowable. They exist in conditions so extreme that our usual concepts begin to break down. What is a surface when speaking of a shell of Planck thickness? Does it even make sense to speak of inside and outside when quantum effects dominate? We use words from everyday experience to describe phenomena without analogues in daily life. We build models based on equations that perhaps aren't applicable in these conditions. This isn't science's flaw. It's its honesty. Science says, we don't know, but we're trying to find out. It doesn't claim final answers. It offers best approximations based on available data. And this is its strength. The ability to admit uncertainty. The ability to say, perhaps we were wrong. Here's a new idea. Let's test it. Gravistars are a proposal. A hypothesis. A possibility to investigate. They may prove real. May prove fantasy. Or truth may lie somewhere in between, objects resembling gravistars but not quite as initial models predicted. We'll learn with time. With observations. With data. The history of science is a history of surprises. We thought Earth was flat. Turns out, round. We thought Earth was the center of everything. Turns out, an ordinary planet around an ordinary star. We thought the universe was static and eternal. Turns out, expanding and has a beginning. We thought atoms were indivisible. Turns out, composed of particles. Which are composed of quarks. Which perhaps are composed of strings. Each time we thought we'd reached bottom, understood the basics, the universe said, not so fast. There's another level. Gravistars are another turn in this endless story. Another reminder that reality is richer than our theories. Maybe black holes are a simplification. A convenient model working in first approximation but missing important details. Maybe real objects are more complex, more exotic, stranger. Or maybe gravastars are a dead end. A beautiful idea unrelated to reality. A mathematical artifact not realized in nature. We don't know. Not yet. But the very fact that we can ask these questions, that we can build models, make predictions, plan observations, this is a miracle. A miracle of human mind, capable of gazing into cosmic abysses and trying to understand what hides there. Why do we call gravastars terrifying? Why deadlier than black holes? Not because of physical danger. No. The terror here is intellectual. Existential. The terror of realizing that the universe isn't obligated to be comprehensible. That it may contain objects and phenomena so strange they challenge our ability to grasp them. Black holes we've mastered. Over a century they transformed from mathematical abstraction into real objects we observe, study, even photograph. They became part of our cosmological worldview. We know how they form, how they evolve, how they influence surroundings. Gravastars though, this is a step into the unknown. They require physics we don't yet fully understand. Quantum gravity. Vacuum phase transitions. Phenomena at Planck scales. They remind us of our knowledge's boundaries. That behind every answer hide a dozen new questions. That the universe is deeper than we can imagine. And there's something eerie in this. Vertiginous. Whenever we think we're close to understanding reality's fundamental nature, something appears that throws us back. Or rather, pushes us forward, toward even greater mysteries. This is scientific progress. Movement from island of ignorance to island of ignorance, with an ocean of unknown between and around them. Gravastars are a reminder that the ocean is vast. That we've only begun to explore it. Gravastars aren't the only alternative to black holes. Physicists are inventive, and over decades many exotic objects were proposed, each with distinctive features. Boson stars, hypothetical objects composed of bosons held together by gravity and quantum effects. Unlike ordinary stars where thermonuclear pressure matters, here stability is provided by Heisenberg's uncertainty principle. Bosons can occupy the same quantum state, allowing creation of very dense but non-collapsing objects. Sounds esoteric? Certainly. But the mathematics works. Equations have solutions. The question is only whether suitable bosons exist in nature and in sufficient quantity. Dark matter? Possibly. If dark matter particles are bosons with right properties, they could form stars. Invisible in ordinary light but detectable by gravitational effects. Fermion balls, analogous concept but for fermions. Pauli exclusion principle prevents fermions from occupying the same quantum state, creating pressure that can resist gravity. Neutron stars are examples of fermion balls, but there are suggestions of even more exotic variants. Quark stars, objects where matter is decomposed to quarks. Neutrons destroyed, quarks free, but not yet collapsed into a black hole. Strange matter predicted by quantum chromodynamics. Possibly stable at sufficient density. Preon stars, hypothetical objects if quarks themselves consist of more fundamental particles, preons. Pure speculation at the moment, but physics doesn't exclude such possibility. Planck stars, objects where quantum gravity effects stop collapse at Planck scales. In some sense similar to gravastars, but the stabilization mechanism differs. Here the discreteness of spacetime at Planck scales matters. Wormholes, tunnels in spacetime connecting distant regions of the universe or even different universes. Mathematically permissible solutions to Einstein's equations, requiring however exotic matter with negative energy density. Stability questionable. Formation, a mystery. Each of these objects solves some problem. Avoids singularity. Conserves information. Provides an alternative to black holes. And each faces its own problems. Uncertainty in physics. Doubts about stability. Absence of observational confirmation. Gravastars are one candidate in this zoo. Perhaps the most plausible. Perhaps not. Time will tell. What if truth isn't that only one of these objects is real? What if nature uses all these possibilities? What if depending on conditions, mass, rotation, composition, formation history, a collapsing star can transform into different types of compact objects? Small mass, neutron star. Medium mass, quark star or gravastar. Large mass, black hole. Or vice versa. Or in any combinations. The universe isn't obligated to be simple. It can be diverse. Can use the full spectrum of possibilities provided by physics. And then the observer's task isn't simply determining what's correct, but mapping all realized variants. Understanding under what conditions each object type forms. This changes perspective. Instead of binary choice, black hole or gravastar, we get a continuum of possibilities. A landscape of compact objects, each with its niche in parameter space. Some simulations hint at such possibility. Show that under certain initial conditions an object resembling a gravastar forms, and under others, a classical black hole. The boundary between them may be thin. A small mass change, a slight difference in angular momentum, and collapse result changes. Nature experiments. We observe results. And try to understand patterns. Does all this sound like pure abstraction? Like physicists' games unrelated to real life? In some sense, yes. Gravastars, if they exist, are so far away they present no immediate practical importance to humanity. They won't change our daily lives. Won't help solve climate change or hunger or war problems. But fundamental science has a way of bearing unexpected fruit. General relativity was pure abstraction when Einstein formulated it. Who could have thought that a century later it would be critical for GPS operation? Quantum mechanics seemed an esoteric mind game in the 1920s. Today half the world economy is based on quantum effects, semiconductors, lasers, MRI scanners. Understanding extreme states of matter and spacetime may lead to technologies we cannot even imagine now. Vacuum manipulation. Control over quantum phase transitions. New energy sources based on exotic matter states. This is speculation, of course. But history teaches, understanding nature's fundamental principles sooner or later finds application. More immediate impact, on our worldview. How do we see our place in the universe? How well do we understand reality? If gravastars are real, this means the universe is even more quantum than we thought. That quantum effects are important not only at microscopic scales but at cosmological ones. That vacuum is not emptiness but an active participant in cosmic dynamics. This reinforces the view of the universe as a quantum system. Not as classical spacetime where quantum effects are small corrections, but as fundamentally quantum reality where classical physics is merely an approximation. This also reminds us of human knowledge's boundaries. We're beings evolved for navigating a world of middle scales, sizes and energies far from Planckian. Our intuition is tuned to this world. When we go beyond its limits, into the very small, quanta, or very large and dense, relativistic, intuition fails. Gravistars show how far we can go using mathematics and logic, even when intuition is silent. They're a triumph of abstract thinking. The human mind's ability to construct models of reality it has never seen and may never see directly. And simultaneously, a reminder of humility. That our models are always approximations. That reality may be even stranger than our boldest theories. There's another reason gravistars matter. They inspire. Each generation needs its big questions. Mysteries that push knowledge boundaries. Challenges requiring the best minds and most sophisticated instruments. For previous generations these were atomic energy, space exploration, genome decoding. Projects that mobilized resources and talents, created new technologies and new science branches. For our generation and the next, the nature of compact objects, quantum gravity, spacetime's fundamental structure. Gravistars are a concrete goal. A testable hypothesis. Predictions comparable with observations. This attracts minds. Motivates students to become physicists. Inspires engineers to build better detectors. And in the process of pursuing these goals, even if gravistars prove fantasy, we advance science. Develop new methods. Discover the unexpected. Because that's how exploration works. We go in one direction and find something completely different. Columbus sought a route to India and found America. We seek gravistars. What will we find? Time will tell. Gravistars don't exist in a vacuum, ironic, considering they're filled with special vacuum. They're part of a broader cosmological picture. And the two biggest mysteries of modern cosmology, dark matter and dark energy, may relate to gravistar physics. Dark energy, the mysterious force accelerating universe expansion. We know it exists because we observe its effects, distant galaxies flying apart ever faster. But what is it? Where does it come from? The simplest explanation, cosmological constant, energy of vacuum itself. Vacuum has non-zero energy density creating repulsive gravitational effect. Sound familiar? This is exactly what happens inside a gravistar. Vacuum in an exotic state with negative pressure. Is it possible that the mechanism stabilizing gravistars is connected to the mechanism determining dark energy? That vacuum phase transitions occurring in extreme conditions of compact objects give us a key to understanding vacuum behavior in the universe as a whole. Some physicists explore this possibility. Build models where gravistar vacuum energy and cosmological constant are manifestations of the same physics. If so, studying gravistars isn't just a question of understanding compact objects. It's a window into spacetime's fundamental nature, into mechanisms governing the entire universe's evolution. Dark matter, another mystery. 85% of universe matter is invisible. We know of its existence by gravitational effects. Galaxies rotate faster than they should if containing only visible matter. Galaxy clusters are held together by greater gravity than visible matter creates. But what is dark matter? Particles. What kind? We build detectors, search for direct collisions of dark matter particles with ordinary matter. So far unsuccessfully. Alternative idea: what if part of dark matter isn't particles but compact objects? Objects that don't emit light or emit it so little we cannot detect them. Stellar mass black holes. Boson stars. Gravastars. If gravastars formed from primordial density fluctuations in the early universe, before star formation, they could comprise a significant dark matter fraction. A population of primordial gravastars scattered through galaxies, creating gravitational effects but practically invisible. This is speculative. Calculations show compact objects can explain only a small dark matter fraction. But even a small fraction matters. Every percent we can explain brings us closer to solving the mystery. The Big Bang. 13.8 billion years ago. The universe was incredibly hot, incredibly dense. Matter and energy in states we can barely imagine. In the first fractions of a second after the Big Bang, in the Planck epoch, the first 10 to the minus 43 seconds, physics as we know it doesn't apply. Quantum gravity effects dominate. Spacetime fluctuates. Vacuum undergoes phase transitions. The very phase transitions that perhaps occur when gravastars form. Studying gravastars, we're perhaps studying early universe relics. Mechanisms active in cosmos's first moments, preserved in these extreme objects. It's like archaeology, but not of Earth, but of time itself. Gravastars are fossils from the Planck epoch. Samples of physics operating when the universe was younger than 1 second. If we can understand gravastars, we may understand what happened in those first moments. How the universe evolved from quantum foam to classical spacetime. What phase transitions vacuum underwent. How matter separated from antimatter. Grand questions. Questions about the origin of everything. And gravastars are one path to answers. Let's briefly immerse in mathematics. Don't worry, we won't use formulas, promise to avoid complex terms. But understanding how physicists investigate gravastars requires at least general understanding of methods. At the foundation of everything, Einstein's equations. 10 interrelated partial differential equations connecting spacetime curvature with matter and energy distribution. Beautiful. Elegant. And extremely complex. For most situations, Einstein's equations have no analytical solutions. We cannot simply solve them like a school quadratic equation. Instead, we build approximations, use numerical methods, simulations on supercomputers. For gravastars, the task is particularly complex. We must describe matter in extreme states, densities approaching Planckian. We must include quantum effects in classical gravity equations. We must model vacuum phase transitions whose physics we understand only partially. This requires assumptions. Simplifications. Model equations of state, relationships between pressure and matter density. Different assumptions give different results. Some models show stable gravastars. Others, unstable configurations collapsing in microseconds. Which model is correct? We don't know. We have no experimental data for such densities and pressures. We extrapolate known physics far beyond its tested applicability. It's like building a skyscraper on shaky foundation. The structure may prove strong, may collapse. Everything depends on details we cannot verify directly. And yet we try. Because this is the only way forward. Build models, make predictions, compare with observations, correct models. Iterative process. Gradual approach to truth. Unable to observe gravastar formation directly or recreate conditions in laboratory, physicists turn to computer simulations. Modern supercomputers are capable of astonishing things. They model galaxy collisions, star evolution, black hole mergers. Each simulation, a virtual experiment where we can control parameters, change conditions, observe results. For gravastars, simulations are especially important. We can set initial conditions, a collapsing star of certain mass and composition. Include various matter equations of state. Add effects of rotation, magnetic fields. Then run the simulation and see what happens. Does a stable gravastar form? Or does it collapse into a black hole? Or explode? What gravitational waves are generated? What electromagnetic signals? Each simulation answers these questions for a specific parameter set. Running thousands of simulations with different parameters, we can map possibilities. Determine under what conditions gravastars are stable and under what they aren't. The problem is simulations are limited by available computational resources. Modeling Planck scales in a kilometer-sized object is an inconceivable task. The scale difference is too great. Therefore simplifications are used. We model the shell as a continuum, ignoring quantum structure at small scales. We use averaged equations of state, not accounting for quantum fluctuation details. Results are informative but not definitive. They show what's possible within our models. But reality may differ. Nevertheless, each simulation is a step forward. Each result, a puzzle fragment. Gradually the picture becomes clearer. Besides numerical simulations, physicists use analytical methods, attempts to find exact or approximate equation solutions. For gravastars with high symmetry, for example, perfectly spherical, non-rotating, analytical solutions can be obtained. They're elegant, give deep understanding of object structure. The Maser-Mottola solution was the first example of such analytical approach. They found a configuration satisfying Einstein's equations, representing a stable object without event horizon. Since then many physicists have developed this work. Added rotation, solutions for rotating gravastars. Included electric charge. Considered multiple shells. Each extension complicates mathematics but enriches understanding. Analytical methods are also used to investigate stability. We can take a gravastar solution and study how it reacts to small perturbations. Is it stable? Or do perturbations grow, destroying structure? This is linear stability analysis, a standard physics tool. It doesn't give the full picture, nonlinear effects may be important, but provides first approximation. Results are mixed. Some gravastar configurations are stable to small perturbations. Others aren't. The stability boundary depends on model details. This is typical for physical systems on the edge of existence. Small parameter changes can shift the system from stability to instability. Nature loves balancing on the edge. Ideas from cutting-edge physics often seep into mass culture. Black holes became movie stars, novel subjects, TV show features. They entered collective consciousness as symbols of the unknown, unknowable, terrifying. Gravastars haven't yet achieved such status. But this may change. Imagine a film or novel where protagonists encounter a gravastar. An object looking like a black hole but not being one. Where a solid surface could, in principle, serve as a landing site, though gravitational tidal forces would tear any ship apart long before reaching the surface. Where inside hides exotic vacuum, whose energy if released could power a civilization or destroy it. Where quantum physics becomes macroscopic and reality's laws distort beyond recognition. Science fiction loves such concepts. They provide rich ground for speculation, for exploring what if. What if a civilization learned to create gravastars artificially? Use them as energy sources, controlling vacuum phase transitions. Or as weapons, threatening to release contents and destroy star systems. What if inside a gravastar spacetime is so distorted that time flows differently? That what seems like seconds inside are millennia outside? Or vice versa? What if gravastars are gateways to other universes, if the exotic vacuum inside connects to different spacetime regions? These are speculations. Fantasy. But science fiction has always been inspired by real science's edge. And gravastars stand right at that edge. Perhaps one day they'll be as iconic as black holes. Perhaps children will grow up learning about them in school. Perhaps humanity's far future will involve interacting with these objects, harvesting their energy, avoiding their dangers. Or perhaps they'll remain a footnote in physics history. An interesting idea that didn't pan out. A path not taken. But for now, they're a possibility. A mystery. A challenge. And mysteries are what drive us forward. They're what make us human. The desire to understand, to explore, to push beyond the known. Gravastars embody this desire. They represent our refusal to accept easy answers. Our insistence that reality may be stranger, richer, more wonderful than we imagine. They remind us that the universe doesn't reveal its secrets easily. That every answer we find opens new questions. That the more we learn, the more we realize how much we don't know. And yet we persist. We build detectors. We run simulations. We make observations. We test hypotheses. Because this is what science is. Not a collection of facts but a process. A way of asking questions about nature and listening carefully to the answers. Gravastars may exist. They may not. The universe will tell us, if we ask the right questions in the right way. And regardless of the answer, the journey will have been worthwhile. Because in seeking gravastars, we'll learn about quantum gravity, about spacetime's nature, about matter's behavior at extremes. We'll push technology forward. We'll inspire the next generation. We'll expand human knowledge's boundaries. This is the promise of fundamental science. Not immediate practical application but deep understanding. Understanding that eventually, unpredictably, leads to technologies and insights we cannot foresee. Einstein developing general relativity had no thought of GPS. Quantum mechanics pioneers never imagined computers. The scientists proposing gravastars don't know what their ideas might lead to. But that's the beauty of it. Science isn't about knowing the destination. It's about the journey into unknown territory. And gravastars, whether real or imaginary, are taking us on quite a journey. Through the mathematics of curved spacetime. Through the quantum physics of vacuum states. Through the observational astronomy of gravitational waves and X-ray emissions. Through the philosophy of what it means for something to exist. This journey challenges us. It stretches our minds. It forces us to question assumptions we didn't know we were making. What is space? What is time? What is matter? What is vacuum? These seem like simple questions. Children ask them. But the more deeply we probe, the more we realize how little we understand. Space isn't an empty stage where events unfold. It's dynamic, responsive, participant in cosmic drama. It can curve, twist, ripple with waves. Time isn't universal clock ticking uniformly everywhere. It's flexible, relative, different for different observers in different gravitational fields. Matter isn't solid stuff. It's concentrated energy, quantum probability waves, fields permeating space. Vacuum isn't nothing. It's seething quantum activity, virtual particles, potential energy waiting to manifest. And gravastars, if they exist, combine all these strange truths into one object. They're where space curves maximally without breaking. Where time slows to near standstill at the surface. Where matter reaches maximum density. Where vacuum transitions to exotic state. They're nature's extreme experiment. A test of physics at its limits. And we're privileged to live in a time when we can actually investigate them. When our technology has advanced enough to detect gravitational waves, to image compact objects, to run simulations of extreme physics. A century ago, this would have been impossible. A century hence, it may be routine. We stand at a unique moment in history. When gravastars transition from wild speculation to testable hypothesis. When we can actually gather data that might confirm or refute their existence. This moment won't last forever. Soon we'll know. LISA will fly. Better telescopes will observe. More mergers will be detected. And then we'll have our answer. If gravastars exist, physics changes. Textbooks rewrite. New research avenues open. Technology eventually follows. If they don't exist, that's also valuable knowledge. It constrains theories. It tells us something about how nature works, that certain configurations, while mathematically possible, aren't realized in reality. Either way, we win. Because we'll know more than we do now. And knowledge, understanding, insight, these are humanity's greatest treasures. More valuable than gold, more lasting than monuments. Civilizations rise and fall. Technologies become obsolete. But understanding nature's fundamental workings is eternal. Einstein's insights about spacetime will be true 1,000,000 years from now. Newton's laws of motion will still apply. The quantum principles we've discovered won't change. And if we discover that gravastars exist, or definitively prove they don't, that knowledge will last forever. This is what motivates physicists. Not fame or fortune, physics rarely provides either. But the chance to add to humanity's permanent knowledge base. To solve a mystery that has puzzled us. To understand something about the universe that no one has understood before. It's a noble calling. A worthy pursuit. And gravastars, deadly or not, terrifying or not, are a magnificent mystery to pursue. They challenge everything we thought we knew about collapsed stars. They require us to think deeply about quantum gravity. They push us to build better instruments. They inspire new generations of scientists. Whether they prove real or imaginary, they've already served a purpose. They've sparked debates, inspired research, driven technological development. And they've reminded us of something crucial: the universe is under no obligation to make sense to us. It is what it is, regardless of our theories or preferences. Our job is to observe carefully, reason clearly, and follow the evidence wherever it leads. Even if it leads to objects stranger than black holes. Objects that seem impossible but might just be real. Objects that embody the terrifying beauty of physics at its most extreme. Gravastars. Dead stars that aren't quite dead. Black holes that aren't quite black. Singularities that aren't quite singular. They occupy the liminal space between existence and non-existence. Between known physics and the unknown. Between what we can imagine and what actually is. And perhaps that's fitting. Because the frontiers of knowledge are always liminal spaces. Places where old certainties fade and new possibilities emerge. Where we grope in darkness, not quite sure what we'll find. This is uncomfortable. Humans crave certainty. We want definite answers, clear categories, firm ground beneath our feet. But the universe doesn't care about our comfort. It is what it is. And if that includes gravastars, objects that violate our intuitions, that challenge our theories, that force us to expand our understanding, then so be it. We'll adapt. We always do. We'll build new models. We'll revise our theories. We'll expand our conceptual frameworks to accommodate new realities. This is how science progresses. Not smoothly, not easily, but inexorably. Each generation building on the previous one. Each discovery opening new questions. Each answer leading deeper into mystery. And gravastars, whether confirmed or refuted in the coming years, are part of this grand adventure. They represent humanity at its best, curious, persistent, unafraid to question everything, willing to follow evidence even to strange conclusions. They remind us why we do science. Not for practical applications, though those eventually come. Not for technological advancement, though that follows. But for understanding. For knowledge. For the sheer joy of figuring out how nature works. Because in the end, what separates humans from other animals is our drive to understand. Our refusal to accept mystery without investigation. Our insistence on asking why and how about everything we encounter. Gravastars are just the latest manifestation of this eternal human quest. A quest that has taken us from caves to cities, from stone tools to spacecraft, from ignorance to enlightenment. A quest that will continue long after we're gone. And somewhere in that future, perhaps centuries or millennia from now, humans, or whatever we've become, will look back at this era and smile. They'll remember when we first asked about gravastars. When we first detected gravitational waves. When we first imaged the shadow of a compact object. They'll see this as a pivotal moment. When humanity took another step toward understanding the cosmos. Just as we look back at Galileo's telescope, Newton's Principia, Einstein's relativity papers. Each generation has its questions. Its mysteries. Its frontiers. Gravastars are one of ours. And whether they exist or not, the fact that we can conceive of them, model them, test for them, this is remarkable. This is the power of human intellect. The ability to imagine possibilities beyond direct experience. To construct mathematical descriptions of objects we've never seen. To devise tests that can distinguish between subtle alternatives. This is civilization's highest achievement. Not our buildings or our art or our literature, magnificent as these are. But our science. Our systematic investigation of nature. Our collective effort to understand reality. And gravastars, these strange hypothetical objects at the edge of possibility, exemplify this effort. They may turn out to be real. They may turn out to be fantasy. But the search for them, the observations, the calculations, the debates, the discoveries made along the way, this is undeniably real. This is science in action. And it's a beautiful thing to behold. The hunt for gravastars has transformed from theoretical speculation into experimental campaign. Across the globe, telescopes point skyward. Detectors listen for the faintest whispers in spacetime's fabric. Supercomputers churn through petabytes of data, searching for patterns, anomalies, signatures of the impossible made real. Consider the sheer audacity of what we're attempting. We're trying to distinguish between two objects that differ by distances smaller than a proton's width. We're trying to detect echoes lasting milliseconds in signals from billions of years ago. We're trying to see structure on scales where quantum mechanics and gravity wage their eternal battle. This isn't just difficult. It's at the absolute bleeding edge of what's physically possible with current technology. And yet we persist, because the prize is worth it. Understanding whether gravastars exist could unlock the deepest secrets of nature. The electromagnetic spectrum tells only part of the story. For decades, astronomers relied primarily on light, visible, infrared, radio, X-ray. These wavelengths revealed galaxies, stars, nebulae, all the luminous phenomena of the cosmos. But they're blind to the darkest objects. Black holes shine only through their effects on surrounding matter. And gravastars, if they exist, would be similarly dark. Enter gravitational wave astronomy. A completely new sense. Not electromagnetic radiation but ripples in geometry itself. When LIGO made its first detection in 2015, humanity gained the ability to hear the universe in a fundamentally different way. The collision of two black holes, or what we assumed were black holes, produced a signal so clear, so unmistakable, that it announced a new era of astronomy. But here's the twist. Every detection since then has been interpreted through the lens of standard black hole theory. We see a massive compact object. We assume it's a black hole. We fit the data to black hole models. And the fits are good. Excellent, even. But good fits don't prove uniqueness. Multiple models can produce similar signals. A gravastar merger might look almost identical to a black hole merger. The differences exist in subtle details, in the fine structure of the waveform, in the late-time ring-down phase. Detecting these differences requires exquisite precision. LIGO's detectors can measure distance changes smaller than 1/10,000th the diameter of a proton. This is incomprehensible precision. It's like measuring the distance to Alpha Centauri to within the width of a human hair. And yet it may not be enough. The next generation of detectors promises orders of magnitude improvement. The Einstein telescope, proposed for construction in Europe, would be 10 times more sensitive than LIGO. Built underground in a triangular configuration, shielded from seismic noise, operating at cryogenic temperatures to reduce thermal vibrations. It could detect mergers across the entire observable universe. Cosmic Explorer, the American counterpart, would feature arms 40 kilometers long, 10 times longer than LIGO's. At these scales, detector sensitivity increases dramatically. The subtle differences between black holes and gravastars become resolvable. The echoes become clear. The truth becomes accessible. But building these instruments requires vision, funding, political will. They're multi-billion-dollar projects spanning decades. And they compete with other scientific priorities, other societal needs. Convincing governments and populations to invest in fundamental physics research is never easy. Yet history shows such investments pay dividends. LIGO itself was controversial, expensive, risky. Many doubted gravitational waves would ever be detected. The project nearly died multiple times. But persistence paid off, and now we have an entirely new window on the cosmos. The same could happen with gravastar searches. What seems like esoteric physics today could become transformative technology tomorrow. The quantum vacuum states that stabilized gravastars might inspire new materials, new energy sources, new ways of manipulating spacetime. Or they might not. We cannot predict where fundamental research leads. That's precisely why we do it. The unexpected discoveries are often the most valuable. Meanwhile, theorists continue refining gravastar models. Each year brings new papers exploring different configurations, different equations of state, different formation mechanisms. The mathematical landscape of these objects grows richer, more complex, more nuanced. Some researchers investigate gravastar interiors in detail. What happens in that exotic vacuum core? Can we describe it using effective field theory? Do quantum fluctuations create structure on Planck scales? Is there a smooth transition from the shell to the interior, or a sharp boundary? These questions connect to the deepest problems in physics. Quantum gravity, the holy grail of theoretical physics for nearly a century. We know general relativity works brilliantly at large scales. We know quantum mechanics works perfectly at small scales. But they're fundamentally incompatible. Merging them has proven extraordinarily difficult. Gravastars exist precisely where these two theories collide. If we could observe them, if we could measure their properties precisely, they might provide clues about how to reconcile quantum mechanics and gravity. They might be Rosetta Stones for quantum gravity. String theory offers one approach to this problem. In string theory's framework, all particles are vibrations of tiny strings. Gravity emerges naturally from string dynamics. And string theory makes predictions about exotic objects like gravastars. According to some string theorists, gravastars could be stable configurations of strings and branes wrapped in complex topologies. The event horizon is replaced by a horizon-scale structure of quantum strings. Information is encoded holographically on this structure, preserving unitarity without the need for a true singularity. These ideas are beautiful, mathematically rich, and completely untested. String theory operates at energy scales far beyond experimental reach. We cannot build accelerators powerful enough to probe string-scale physics directly. But cosmological observations, including potential gravastar detections, might provide indirect evidence. Loop quantum gravity takes a different approach. Instead of strings, it posits that spacetime itself is quantized at Planck scales. Space is not continuous but composed of discrete quantum units. Gravity emerges from the dynamics of these fundamental quanta. In loop quantum gravity, the singularity problem disappears naturally. When matter collapses, it cannot be compressed beyond a certain density, the Planck density. Quantum geometric effects create a repulsive force, halting the collapse. This sounds remarkably like the Gravistar scenario, though the detailed mechanisms differ. If loop quantum gravity is correct, every black hole might actually be a Planck star, a close cousin of gravastars. The observational signatures would be similar: no true event horizon, a surface of extraordinary density, preservation of information. Testing these theories requires observations of the most extreme objects in nature. And that brings us back to gravastars. Whether they exist as pure vacuum condensates, string-based horizonless objects, or Planck stars from loop quantum gravity, the observational challenge is similar. Find the subtle differences distinguishing them from classical black holes. The search extends beyond gravitational waves and electromagnetic observations. Some physicists propose using cosmic rays, high-energy particles bombarding Earth from space. The most energetic cosmic rays have energies exceeding anything we can produce in accelerators. Where do they come from? One possibility: the surfaces of gravastars. When matter strikes a gravistar's shell at relativistic speeds, the collision would release enormous energy. Particles would be accelerated to extreme velocities. Some would escape, traveling across the cosmos, eventually reaching Earth as ultra-high-energy cosmic rays. If this is true, the energy spectrum and composition of cosmic rays might encode information about gravistar properties. By studying cosmic rays in detail, we might indirectly probe these exotic objects. The Pierre Auger Observatory in Argentina, with its array of detectors spanning 3,000 square kilometers, collects data on the highest energy cosmic rays. The Telescope Array in Utah does the same. Together, they're building a picture of the most violent processes in the universe. Could some of those processes involve gravastars? Possibly. The data is complex, the interpretations uncertain. But it's another line of evidence, another way of searching for these elusive objects. Neutrinos offer yet another window. These ghostly particles barely interact with matter, passing through planets and stars almost unhindered. But in the most extreme environments, supernovae, black hole mergers, perhaps gravistar collisions, neutrinos are produced in vast numbers. IceCube, buried deep in Antarctic ice, detects neutrinos from cosmic sources. When a high-energy neutrino strikes ice, it creates a characteristic pattern of light. By analyzing these patterns, physicists can trace neutrinos back to their sources and infer the physics occurring there. If a gravistar merger or destabilization produces distinctive neutrino signatures, IceCube might detect them. Combined with gravitational wave observations, this multi-messenger astronomy could definitively identify gravastars. The synergy between different observation methods is crucial. No single technique provides conclusive evidence. But when gravitational waves, electromagnetic signals, cosmic rays, and neutrinos all point to the same conclusion, confidence grows. The case becomes compelling. This is how modern astrophysics works. Not through single dramatic discoveries but through patient accumulation of evidence from multiple independent sources. Each measurement constrains the possibilities. Each observation narrows the parameter space. Slowly, truth emerges. Consider the recent history of neutron-star mergers. In 2017, GW 170817 was detected by LIGO and Virgo. Gravitational waves announced the merger. But within seconds, the Fermi satellite detected gamma rays from the same location. Then optical telescopes saw the kilonova, the radioactive afterglow. Then X-rays. Then radio waves. 70 observatories on all 7 continents and in space observed this single event. The combined data revolutionized our understanding of neutron stars, heavy element formation, gamma-ray burst mechanisms. One event, observed comprehensively, yielded more insights than decades of single-wavelength astronomy. Imagine similar comprehensive observations of a gravistar event. If we could capture every aspect, gravitational waves, all electromagnetic wavelengths, neutrinos, cosmic rays, the resulting data set would be unprecedented. We could test gravistar models with exquisite precision. We could distinguish between alternatives. We could potentially solve the mystery definitively. But this requires coordination, preparation, rapid response. When LIGO detects a promising signal, alerts must go out instantly to observatories worldwide. Telescopes must slew to the source location within seconds. Data must be collected before transient phenomena fade. The infrastructure for this exists now, refined over years of practice. But it can always improve. Faster alerts, more telescopes, better coordination between different observer communities. Every improvement increases our chances of capturing that perfect observation, the one that reveals gravistar nature unambiguously. Some physicists argue we should look not at violent merger events but at quiescent objects. Many galaxies harbor supermassive compact objects in their centers. We call them supermassive black holes. But are they? If even a fraction are gravistars, they should exhibit subtle differences in their quiescent emission. The accretion disk structure would differ slightly. The X-ray variability would have different character. The radio emission would show particular patterns. These differences are small, requiring long-term monitoring campaigns. But patience could pay off. By studying multiple galactic centers over years, accumulating vast datasets, patterns might emerge. Statistical analysis could reveal population-level differences between true black holes and gravistars. This approach complements event-based searches. It's less dramatic but potentially more reliable. Rare violent events are exciting but also uncertain, too many variables, too much chaos. Steady observations of quiescent objects provide cleaner data, easier interpretation. The Vera Rubin Observatory, soon to begin operations in Chile, will survey the entire visible sky every few nights. Over a decade, it will create an unprecedented time-domain map of the universe. Every object that varies, moves, or changes will be catalogued. Among those objects will be thousands of galactic centers, millions of compact object candidates. The data volume will be staggering, hundreds of petabytes. Making sense of it will require advanced machine learning algorithms, automated classification, intelligent filtering. But hidden in that data might be the signatures of gravistars. Patterns invisible to human eyes but detectable by properly trained neural networks. The faint statistical fingerprints distinguishing different populations of compact objects. Artificial intelligence is revolutionizing astronomy. Modern telescopes generate more data than humans can possibly analyze manually. Machine learning fills the gap, finding signals in noise, classifying objects, identifying anomalies worth human attention. For Gravistar searches, AI could be transformative. Train neural networks on simulated Gravistar signals. Teach them to recognize subtle features in gravitational waveforms, in light curves, in spectral data. Then unleash them on real observational data. The networks might find what humans miss. They might identify candidate events that don't quite fit standard models. They might reveal patterns we hadn't thought to look for. Of course, AI has limitations. Networks can hallucinate, finding patterns in random noise. They can be biased by their training data. They require careful validation, skeptical evaluation. But as tools for exploration, they're invaluable. The combination of AI and massive datasets might enable population studies impossible by other means. Instead of identifying individual gravastars, which might be vanishingly rare or observationally indistinguishable, we could characterize populations